today. Well, not at home. He is a PhD candidate at Stanford University in the Department of Geophysics. Before arriving at Stanford, I'm told he did his bachelor's degree in Ames, Iowa, at Iowa State University with a Cyclone.
That's right.
After that, he moved to University of Wisconsin-Madison. That's right.
Yep.
And now he's at Stanford.
Much better.
Yeah, we're happy to have Ian here. He is a world-leading expert at a PhD candidate level in size interfacing deep machine learning with seismology. I think we'll talk about this stuff today. Excited to hear about that. And so if you could with me, help get you going.
Thank you very much. Really appreciate that. It's great to be here. I grew up in Colorado, so it's kind of nice to be back in like the mountains, you know. So this is fun. And yeah, I'm gonna talk about this project today on deep learning enhanced catalog for Northern California of earthquakes. Some of it's a little technical, like the methods, but hopefully it'll be still accessible to those who aren't maybe so familiar with building earthquake catalogs. So yeah, the quick overview is I'm just gonna talk about earthquake detection problem, review this approach we're using, which is based on graph neural networks, talk about Northern California, and then kind of go into some of the results. So traditional earthquake detection pipeline is kind of broken into several pieces where essentially, for starters, we have seismic sensors, you know, seismometers placed around the world, and we want to collect data on those and then convert it into a record of when and where earthquakes occurred. And so you do some pre-processing of the data, filtering, stuff like that. Then you do what's called phase picking, which is you kind of determine when does a P or an S arrival or other phases show up on your stations. And then we do what's called association, which is kind of the hard part, in my opinion, where you have to kind of figure out how to combine those picks on different sensors and determine, oh, this subset of picks is from one earthquake, this subset of picks is from another earthquake. And it gets tricky because there can be a lot of false earthquakes and other kind of complicating factors. Maybe that pick is from a train and the other one's from an earthquake, and you have to kind of disambiguate all of this. So that's association, and it's very coupled with the problem of locating the earthquake itself. And then you can characterize the events like magnitude and so forth. So the association problem, kind of a schematic example of it, is what's shown here on the right, where essentially what you have is a record of seismic waveforms coming in on your network. So each of these is just a little cartoon, synthetic seismogram. And at first, on the left-hand panel there, we don't know how many earthquakes there are. We just have a bunch of picks across the network. The y-axis is the station number, so you're just kind of arranging your stations in some way. And the x-axis is time, and so you have all these arrivals, but you don't know what's going on. So association is converting it to what's on the right, grouping those picks into the set of assigned events where you're like, this is a set of picks that all comes from one event, this is another set of picks that comes from a different event, so forth. And again, there's a lot of challenges, like we don't know the number of events ahead of time, so you need to figure that out while you're doing this process. There could be overlapping events like you see there, like multiple are coming across the network at the same time. And so a lot of data challenges. And also there can be way more than 10 stations, as you're going to see today. So you have to deal with that too. So here's just a kind of classic example of how you might solve this problem. Essentially, it's based on the idea of what's called back projection. So what you can do is you can try to search for a point in space. So there's a latitude, longitude map, so spatial map, that if we were to nucleate the source at that point and at a particular time, it would produce a set of arrival times that match the observed arrival times on your network at the right times. So for instance, like sound waves, you know, you're familiar with that. Like I speak now and the waves travel out and it shows up at all of you at a different time. Well, it's true in the earth as well. When an earthquake occurs deep in the underground, it's going to produce waves and it's going to propagate at a certain speed and show up at these different seismometers. So in theory, you can find what is that likely source location that had a source nucleated there, it would produce the set of arrivals we're seeing on our network. So you can turn this into kind of like a grid search algorithm, essentially, where you go through and you find all the points in space that kind of look like they fit a lot of data. And so get a map that looks like this, where, yes, the true earthquake has the biggest bright spot, if you want to call it that, right where the earthquake was, but it has this kind of interference pattern elsewhere. And it's a little hard to see because of the color scheme here on the screen, but that's a pretty complicated looking interference pattern that shows up even for one earthquake with perfect data. So what happens then is when you have multiple earthquakes at the same time, so what I was showing it on the left is just when I back project earthquake number 1. But you don't know the number of earthquakes ahead of time, so you have to deal with all of them at the same time. And when you do that and you make these back projection images, this grid search scheme, you get a really complicated image like shown on the right. And now you can get these false maxima that are really bright but there's no earthquake there. So like there's 3 big bright spots. You could argue there's kind of more, but there's at least 3. And that one in the middle that I don't have an arrow pointing to, that's not a real earthquake at all. This is synthetic data, so we know the ground truth. That is a place where the waves from 2 different earthquakes are both constructively interfering, essentially. At that, it looks as if that's what's going on. So there's this intense ambiguity in the phase association problem, and that's what we're trying to avoid. So, and solve this issue, basically. Take the data and figure out, yes, there were 2 earthquakes, not 3, not 4. There was 2, they were at these places and at these times. So if you can do that, then you can build an earthquake catalog, and you can then do interpretation of seismicity and do all these other important things you care about, like understand fault maps and potentially other geologic things. So the way we approach this is with a deep learning model, and I'm not going to go too into the details of it, but it's a graph neural network. And so graphs are, a pretty classic math technique where you have a set of nodes and you have edges connecting those nodes together. So in our case, you can kind of step back and realize, well, the fundamental data we're working with is station data in a sense. So we have seismic stations in space. And so what I show here on the top left is a set of stations from Northern California. And we treat these as nodes, and we draw edges between them. We have edges connecting the nodes. And when we're doing this data processing scheme with our neural network, these stations are now allowed to communicate with each other, share information. So basically, they can communicate very important things, like one station can realize I'm observing a pick, and this other station near me is also observing a pick. Another station near it is also observing a pick. Potentially, they're observing them at a similar, at let's say a lag time that makes sense for theoretical move out propagating through the Earth. So we can find those kind of coherent signatures of events on its own because it's allowed to transmit information across the graph structure. And that's kind of just different than a lot of neural network applications, because if you just use, let's say, a normal fully connected neural network where you just plug everything in at once and there's no inherent graph structure, it wouldn't be able to easily find those kind of subtle signatures. The graph like kind of distills the structure you're working with, like the important interactions, and makes it a lot easier to learn and kind of not have like obvious failure modes in a sense. Anyways, that's our setup. We have another graph for the spatial region, so kind of points we're checking where the earthquakes are. It's not actually, we can still find events everywhere. These are just reference points we're kind of measuring things at. But we can find events everywhere, not just at those source points, the red ones. Then we pass in our pick data. So this is the station index on the y-axis, time in the x. So it looks really complicated. Those are arrival times of potentially P and S waves or other things. And what we want to do is map it to the prediction, which is on the right-hand side. We have 2 predictions that we output. One is the space-time heat map of where we think events occurred. So like literally the location and origin times. That's what's shown by this big bright yellow spot. You can kind of contrast this output with what was shown on these plots. In some sense, I'm trying to do the same thing. I just want to predict something that doesn't have that interference pattern everywhere else in space. I just only want the bullseye where the earthquake is, nothing else. That's what we're training our model to do. And so the output is a lot easier to work with. It's just a single, bright spot, not the interference pattern. At the same time, it solves another kind of more important problem, which is it figures out which of the input picks in this big panel are the real ones associated to the events that it's identifying in those heat maps. So it finds that the input, this huge set of input picks, only a very small number of them are actually the P waves or S waves for either of the 2 earthquakes. And so basically, those 2 panels on the right-hand side show the predicted P arrivals assigned to that event there, and the predicted S arrivals assigned to that event there. There are different times, but we can separate them and get them both extracted from the data set. And just as a word of caution, I do these plots kind of a lot where it's like station on the y-axis, time on the x-axis, the dots are the pick times, and then the curve you see, that blue curve and the red curve, that's the theoretical arrival times of the P waves and the S waves from the source location in yellow. And because the stations are randomly positioned in space, that theoretical arrival time curve has to kind of bounce around a bit. There's no monotonic arrangement of stations, right? So that's why the curve looks a little weird, but this also emphasizes why the association problem is hard. It's even hard to visualize the data in the first place. But this is kind of one approach to doing that. And now, that's kind of our setup. We can train this GNN with a lot of data, simulated data. We simulate realistic move-outs, and then we try to train it to correctly identify which picks are associated to which events and how many events there are and where the events are. So the reason we use graph neural networks is I kind of already said it, but they just have a very natural structure for handling things like seismic network data. Other classic machine learning models like CNNs or RNNs just don't have that flexibility. Those treat what's kind of called Euclidean data, where the data is regularly sampled in space. But here, it's not regularly sampled in space. So graph neural networks are kind of the go-to deep learning approach for handling non-Euclidean data, which I think is very important for seismic network processing, but a lot of other problems in geophysics or geology potentially as well. Because you deal with structures that aren't, super uniform a lot, like fault networks and things like that. So anyways, GNNs are quite great, and that's what made this work. So our original application was we try to use this model and see, even though we've trained it on synthetic data, can we detect real events in California from known events that the really smart network operators have already put a ton of effort into identifying. So what we did is we took 500 random days between 2000 and 2020 of our trained model, only trained on synthetic data. And then these are the event distributions that we consider for those 500 days. So these are the ones that occurred according to the USGS or the NCEDC in Northern California. And we just kind of asked the question, can we redetect these events using our model? And the answer was that we could. And so we could basically get, in this case, 95% of them, 96% of them. And so you see that the black dots are the original locations in the NCEDC catalog. And the red are the output once we detected these events. And so they match quite well. The green lines connect the paired events. So it's the same approximate location and origin time within just plus or minus a second or two. And yeah, so it kind of worked. And then what we checked is, can we get new events, not just the ones that they detected? And the answer to that is also true. Partly that's because we're using a different picker than them. So they have pickers that are not deep learning pickers. And the pickers, the picking of PNS waves has also improved recently using deep learning methods. So that's why we can get more events, because we have more picks. But you need a good associator to use that data correctly. So that's what this does. And basically what this shows is when we applied it over 100 days continuously, we found that we could get way more events than them, about 4 times more. And they also go to lower magnitudes of completion than the reference catalog. So the reference catalog is in orange, and essentially they only report events greater than magnitude 1. But when we calculate the magnitudes of the new ones we're detecting, they're smaller. That's exactly what we would expect, right? If something had gone wrong in our processing, we're creating fake events, which is actually kind of easy to do if you're not careful, we wouldn't end up with a realistic magnitude distribution, which is that the ones we're getting are small events. So if we're going to get new events, they should be small, and that's what we're detecting. And that's because the networks, the established network operators, they can pretty much guarantee they're not going to miss events above a certain magnitude, like 2 or something, 1.5 in this case. But they do miss all the ones below that. So anyways, these new approaches can allow us to get the smaller events. And on the right is just a count of events in time. This was during an aftershock sequence. So in time, spiked up right after that magnitude 4.6 occurred, and we see it decay afterwards, kind of like an Amori decay curve. So yeah, it's just kind of a proof of concept. This was the early results. But we wanted to then scale to larger domains and build a big catalog for Northern California. The region I showed before is not really that much of California. This is kind of just like a little bit around the Bay Area right in the middle, plus or minus a few hundred kilometers. But in this new application, we're interested in pretty much, not the whole state, but like everything north of like Garlock Fault, essentially. It's like the Ridgecrest area, which is this fault. So we're pretty much interested in everything north of that. And now the problem gets a little harder because now we have way more stations. We have about 900 stations. It's not just computational cost that goes up with more stations. There's a fundamental ambiguity of, again, like which sets of picks make sense for an event. If I were to, let's say, here's an event, but the set of picks I'm going to assign to that event are totally randomly distributed on this map, there's no spatial coherency, that would be an unrealistic earthquake. Because a realistic earthquake nucleates in one place, energy decays away from it. So the only places you should see that event are essentially the nearby stations. And so whatever pattern you get, whatever set of stations you assign to that event should be kind of spatially coherent. And when you have 900 stations to work with, it's kind of hard to kind of guarantee that's going to be the case. Anyways, that's kind of part of the challenge, but we took the same approach. We turned this set of stations into a graph by connecting each station to several of its nearby neighbors. This is kind of like a hyperparameter. You sort of have to choose ahead of time, like which edges do you add. But the key is that you essentially want to connect nearby stations to each other because those are the ones that are going to directly be communicating relevant information. And also you need to keep in mind that when you use a GNN, yes, this is the set of stations that are going to directly interact with each other and share information. But when you do multiple rounds of what's called graph convolution, that receptive field gets to expand more and more. So even though we're imposing a fixed set of which stations are connected right now, after 2 or 3 rounds of graph convolution, each one can start sharing information with more and more distant stations. So it's not like super sensitive to this choice. In fact, like I could use 8 or 15 and we'd probably get a pretty similar result. So that's a good thing. It's not overly sensitive to this hyperparameter. But still what makes a graph neural network is that we have a graph here. And then we take the spatial region we're interested in, which is this whole area. The blue is kind of faded. You can barely see the state. But we again turn this into a graph by connecting these nodes to their nearest neighbors. So it's the same setup. We have 2 graphs. They're much bigger than they were before. And yeah, that's the idea. There's some computational costs related to this, but we kind of were able to get around that. And I'm going to skip that part. It's related to which pairs of these that we consider. But anyways, once we step back and we look at the pick data for this region, for these set of stations, it looks quite messy. So this is an example of just an hour of data, an hour of picks across that set of 900 stations for just a random time period, any day of the year. This is what it looks like. And so those blue and orange dots are the predicted P and S arrivals from a deep learning picker. And we want to convert this into a catalog. So the first thing to note is that there's a lot of picks. There's like over 100,000 each day across this network. And also just kind of that there is a lot of interpretable structure in here. So when you plot it like this, the first time you see it, it looks horrible. It's kind of horrendous. But it turns out to be really useful to plot it this way because for starters, when you see those little bands, those little groups, well, those are essentially earthquakes. That means you're looking at a set of picks that shows up on a similarly located set of stations at a similar time. The only thing that really does that is either an earthquake or a blast, maybe a few other things. And what's interesting, though, is if we take this data and we look, where are the events that the NCEDC, so the Northern California Earthquake Monitoring Center, reported earthquakes occurring at? It's just these 3. So the curves, the blue and the red, are the predicted move-outs. And it's kind of hard to tell, but they line up really well with these clusters here. So the curves all kind of go to the same place around this region. And it picks out those events. But the question is, are there more events in there? We don't want to just get those ones. As you can imagine, there is, but we're going to come to that. So moving on. So now I'm just going to show some examples of how it works for individual events. So if we take a magnitude 1 that's happening kind of right in the Bay Area, this is the output of our model, essentially. It's predicted a location here. And what it shows on the left-hand side are the set of associated stations to that event. It's the subset of stations that we have assigned a pick to that event. So the red ones we've associated. And notice how they're pretty much all right next to the earthquake location. That makes sense. Again, if it was randomly positioned, that would be very suspicious. Because it doesn't make sense with respect to the attenuation of energy from the source location. But a lot of associators, a lot of the other associators out there will give you that kind of result if you're not careful. In fact, they'll just give it to you because it's really hard to avoid that issue. The graph neural network, because it's able to combine information between stations, it has this kind of sense of coherency among the stations. So whenever you get an association result, a lot of times it's like this good grouping. So here's a magnitude 1. On the right-hand side, it's the associated picks for that event. In this case, it's oriented by time, so it just moves out in one direction. Here's a magnitude 2 for basically the same location. So you can see the aperture of associated stations grows, and the set of picks we see getting assigned grows as well. But it's still spatially coherent. It's not adding random picks at different parts of the network to this event. That's kind of the key thing. Then here's magnitude 3. So basically same place, and you can see how it's just adding more and more stations, but in a very kind of physically plausible way. And now here's a different location. So here's up at the Mendocino Triple Junction, Pacific Plate, North American Plate, meet, border plate. And there's magnitude 1, there's magnitude 2, there's magnitude 3. One thing that's kind of cool about this case is you can see there's converted phases from this location. So on the right-hand panel, we see our associated P waves, the blue ones. our associated S waves, the red ones, but there's this coherent set of picks showing up right here that we're ignoring, we're avoiding it. But what those picks probably are converted phases between P and S waves, or potentially some other kind of mantle refracted wave. Probably converted phases. But it's just kind of interesting because we wouldn't really see this unless we plotted the data in this way. Those picks would have just been kind of buried in the noise in a sense. But now we can see that our deep learning pickers, even though they're claiming they're giving us P and S waves, they're actually kind of sometimes giving us converted phases as well. Now here's one more place over kind of by the California and Nevada border, magnitude 1, 2, and 3. But the point I kind of want to emphasize also is that look how subtle the signature of a magnitude 1 is with respect to the size of our network. We are associating magnitude 1 at this point over here. We've assigned a set of stations, and my model is not perfect. It accidentally added 2, but it could have added way more than that. But notice that it's like literally like 7 or 8 picks, and it's ignoring every other pick you see there. It understands that those ones aren't related. So that's the hard part, is it's finding a really tiny signature of something among a huge set of possible things, a bunch of picks. And the only way it can really do that in this case is that it's using that graph idea. The stations are talking to each other. So those ones understand we all see something similar at the same time. That's the key. And yeah. So that's kind of interesting. And there's magnitude 3. So just now you have picks across like the whole network essentially. So when we did this approach, we built our initial catalog using this routine. And we've only worked on 2023 right now. So this is the catalog we get out, the initial one. And the color scheme here is depth. So basically yellow and green are kind of mediate depth, shallow essentially. And blue is deep. And so you see that we get the expected structures we expect. What we have is like the San Andreas fault through here. Kind of hard to see at this scale. Other Bay Area faults. The Mendocino triple junction way up there. It's deep there because you have a subduction zone there. And then you get some events throughout the Sierra Nevadas and Nevada. Another thing I want to emphasize is that when we trained our model, we trained on synthetic data. And the distribution of source locations we use in the synthetic data has no awareness of where these faults are. It's completely uniform in space. So when we train it to detect events literally anywhere with no bias to where the faults are, and then we apply it, and we end up with locations exactly where the expected faults are, it's a helpful confirmation that it's doing something realistic. Because it was not told to do this. That's a little different than some machine learning models where you just trained, let's say, on the real data. If we're training on the real data, then it's going to be quite good at recreating that real data. In this case, we did not. We're training on synthetic data that doesn't know the source locations of faults, but it's recovering them. That's kind of a very important aspect. That's just a different way of looking at the catalog, different color scheme. But also, it's a little hard to just show the catalog all at once. So it's a little helpful to kind of look at it over different time intervals. So here's a 10-day version of the catalog, first 10 days. You see there's just a couple events here and there. That little cluster in the middle, that's the Geysers geothermal field. It's like the most active geothermal field in the world, I believe. And about 50% of all the events we detect come from that exact spot. It's a little hard to tell because they just overlap each other, but about 50% of the seismicity is from the geysers. The other area is the Mendocino. In this 10-day interval, there was a magnitude 6, if I'm not mistaken, at the start of that interval. And that's why you see a lot of events up at the Mendocino, because you get the Mendocino magnitude 6, but then also a lot of aftershocks. Now, if we look at 100 days, it looks like this. So now you're really starting to fill in the seismicity everywhere else because you're just getting more events over time. But it's kind of coherent with the pattern that came before. Especially true when you go from 100 days to 365 days. So it kind of shows that what we're doing is like stable. You know, if let's say you went from 100 to 365 and the pattern totally changed, that would be a little concerning because seismicity is sort of stationary. I mean, it has non-stationarity to it, but really in general, you get earthquakes where they're expected to be most cases. So it's cool. It just kind of shows that we're able to recover a catalog where we expect it to be. And this is, again, this is about 3 times more than the reference catalog, the NCEDC. So just to zoom in on some places, here's the Bay Area faults. The orange are the NCEDC locations. The blue are ours. You can see that, A, we have more events, so there's going to be more scatter to begin with. But also, there's some kind of differences. Like we have a little bit of a systematic offset on this part of the San Andreas fault. We know why that's there. There's a velocity model contrast across the fault. And we're using a 1D velocity model that doesn't account for that. So you kind of get a shift because they are more careful about their velocity model. And this other thing, station corrections that some of you might be aware of that kind of helps account for these biases. Either way, it's everywhere else is quite consistent, our locations with theirs. And here's the Nevada, California border area, Sierra Nevadas. Here, kind of cool to see the seismicity is a little bit more scattered. Not as many continuous strike slip faults, but some kind of patchy seismicity. Here's kind of the southern region, same story. Now, another cool thing though is kind of looking at these events in time. So, and magnitude as well. So here's just two test cases we looked at. Zoomed in though back to the kind of the central Bay Area. And what it is in this case is the Napa Valley earthquake 2014. So this is magnitude 6 that occurred in Napa Valley. So even though I said our catalogs for 2023, we have experimented with other time periods as well. So we did these cases just to kind of check. And what's shown on the right is a heat map of our event density distribution. And the red square is the hypocenter of the Napa Valley earthquake. So you see that we're getting a lot of events precisely where they should be. The other bullseye or, dense area you see further north, that's again the Geysers geothermal field. So that place is just always active, always a bright spot in any density map you create. And it's kind of important to recognize that if we're going to detect events in Napa Valley and at Geysers, they're both going to have events at pretty much the same time. And there's going to be a lot of them. And so our algorithm has to be able to correctly separate them out. And basically 3 or 4 years ago, everyone was like struggling with this fact. Like if you have an aftershock sequence, you run your associator, it kind of breaks. It starts combining picks falsely between random combinations of stations and locating them falsely at the same time. And so basically this result kind of helps us verify that it's pretty much not doing that. Obviously it still will, maybe 1%, 2% of cases, but it's like a small fraction. And that's really important. And yeah, so there's event counts in time, there's event magnitudes in time, but it's a similar story as I showed before. The new events we get are the blue ones. The NCEDC, the reference catalog is the orange, and we're getting new events that are smaller magnitude. And then here's a different case. This is the San Ramon Swarm 2015. So it's not a main shock aftershock sequence. It's a swarm, so they behave a little differently in time. But what we see is that the event rate in time kind of goes up and down, up and down. Magnitudes, again, we're getting new magnitudes that are small. But the takeaway is that we're getting our locations at the locations we expect. So the red square there is the nucleation point of this swarm that was identified by USGS or the NCDC. And then that heat map is ours. So clearly we're detecting events right where they should be at the right time. Yep. So that was kind of the initial catalog. And it's pretty similar to the updated catalog. But here's what are called the Gutenberg-Richter distributions of these two catalogs. So this is where we kind of do a statistical count of the number of events we get for each magnitude bin. It's a cumulative distribution in this case. And the key point of doing this is you want to make sure that our cumulative distribution matches up with the one we trust, the NCEDC catalog. So if you look at these Gutenberg-Richter distributions, above a certain magnitude of completion, they're pretty much consistent. So essentially around like 1 or so, these two curves are quite consistent, which means that we're not like artificially predicting big events that are larger that they say don't exist, which again would be very suspicious. We're only predicting new events that are smaller. So that's why our curve, the orange one, goes to lower magnitudes than the blue one. So it's just kind of a way to quantify like the number of events we're getting and if they make sense. And another advantage of doing this is, let's say you run your algorithm and it breaks, something goes wrong. You start building a lot of false events. This will typically show up as our curve, our Gutenberg-Richter curve, would just be offset to the right compared to the reference one. Because we're just adding in a bunch of false events, we're going to have more at every single magnitude level, and it will shift the curve. So sometimes you run this, and if you're not careful, you'll see that, and then you have to go back and figure out what's going wrong. But anyways, it was okay. And then we went through quite a lot of effort to improve this catalog, because 2.8 times is not as much as we thought we could get. Thought we could get more than that. So yeah, it's somewhere between 4 and 5 times. It's actually kind of 4 in the most recent version, but yes, it's in that ballpark. But again, you see the new events we get extend to lower magnitudes, and above a certain magnitude completion, the two catalogs agree quite well. So I think it's, if you think about it, those are kind of the factors that kind of give some validity to this. We're getting events where we expect them to be. We're getting events at the same times we're expecting them to be, at those aftershock sequences. And we have magnitudes that make sense. And if you can't kind of verify that all three of those things are true, then, you could be making false earthquakes. And that's like the thing we're trying to avoid. It's very easy to run these algorithms and end up with false earthquakes, especially when we're in an area of more and more data quality, like more and more data, and these deep learning pickers, which give us way more picks. So yeah, it's just very important that we're not making false events. We don't want to confuse the analysts or confuse people interpreting our seismicity. So yeah, that's why we go through these checks. Anyways, here's the increased catalog. And I don't really need to emphasize this, but it looks very similar to the previous one I was just talking about, but it is almost 2 times as many events. And what's great about that is it's 2 times more events, but not an obvious increase in like randomly scattered events. That would be another failure mode. Is if we got 2 times more events, but they're just randomly positioned in space, well, that's not good either, right? Because they're not real. So to emphasize that fact, it took me almost like 2 or 3 months to go from what's on the left to on the right, because I messed up some things along the way. And here's what it looks like when you kind of mess it up. So that's an example of it not working. And what's going on here is in a lot of places, it's still working and pretty consistent. But in one place in particular, you can see something going horribly wrong. And it's right here. So you might wonder, why is it going so wrong right there? And what do we do to make it do this? So there's 2 explanations for that. Essentially, I changed something in my training data that made the combinations of stations that I'm saying, this is a real event in my training data, they no longer made sense. I kind of accidentally did this thing. I was deleting picks too much. And so what happened is I was basically saying, here's a real event, but the set of stations assigned to that event are pretty much randomly distributed in space. So once I trained it to say, oh, you can make events out of that, like I can add a station there, station there, station there, but none of the stations in between, it started doing that, and then it was creating false events. And what's interesting, that's what caused it. And to some extent, I was training it to detect too many events. I was training it to detect something like 4,000 events a day, when in reality, we have like 200 events a day or 300. So it was a little extreme. But the main reason was that breakdown in the geometric component. I was not giving it geometrically reasonable combinations of stations. But also the reason it breaks right there is because that's the place we have the most stations. So that's kind of right in the Bay Area. And so it's the combination of those 2 factors. We have a lot of stations there, and now it knows they can combine random stations that don't really make sense. And so those 2 things came together, and it created a bunch of false earthquakes. And how I kind of discovered it is, one, you look at it and it looks bad, but I always don't know I don't necessarily know what is the right answer. That's the thing. We don't know what the right answer is. This is raw data. We don't technically know what the ground truth is. But, it looks suspicious for this reason. It's not really lining up with the faults. But the other key giveaway was that when I looked at the Gutenberg-Richter distribution, those lines that are supposed to line up with each other, I had the significant offset. So, yeah. I think it's just important to point out that, it's not always going to go correctly in really any modeling approach, but especially with deep learning, you have to be careful about, the training data and how it's going to influence your final result. But anyways, we fixed that, and that's how we ended up with this increased catalog. You see the event distribution in that part near the Bay Area goes way down back to normal. And yeah, that's important. So when we compare another thing we compute is this is the spatial magnitude of completion. So we might say, oh, we have all events above a certain magnitude, but really it's a function of space. These are different station coverage in each area. And so here's just an example. Coworker I'm working with, or another grad student, he put this together based on this catalog, and he's just comparing. The left-hand side is our new catalog, and the right-hand side is the NCEDC catalog. And so you see that essentially we're just filling in. I think the color scales are slightly different. No, they're not. But basically, we're improving the recovery rate in most places, especially kind of a little bit throughout the Bay Area, definitely up north of the Mendocino Triple Junction. I don't know quite why that is. I think it's because the stations are more sparse there, and so our algorithm, for some reason, more effective there than the default algorithms. And kind of true as well throughout the Sierra Nevadas in the north. So kind of important just to know, where are we sensitive to events, and this is one way to visualize it. Now, I mentioned this earlier. I said, here's the raw picks, And when we look at the NCEDC reported events, it's these ones right here. So those picks do have move out curves that line up with them. I trust these events, but they're missing a lot, right? So we just built a catalog that has more events. What does that look like? Well, that initial catalog that has about 2.8 times more events, I'm going to add some move out curves. So it's these ones. And it's kind of hard to tell, but like especially in that one on the right, you can see it's quite clear. If I plot the move out curve, it lines up with those set of picks. The clustered one right here. And again, this is not a perfect visualization tool because we're taking a randomly distributed set of stations, quasi-randomly, and putting them onto a 1D axis, the y-axis. That doesn't work. you don't preserve all the geometric relationships. But those set of stations are right next to each other, so they kind of end up at a similar station index because I sort it latitude. And so you can see that it lines up. So that was the initial catalog, and then when we add this updated catalog, you get even more events. Now you can get up to like this number. And it's pretty hard to tell on this scale if these are real, but in a lot of cases it is. And really what you need is you need to be interactively visualizing the data. You need to have like a plot up and you can zoom in, and you zoom in and you can verify that like, oh yeah, there really is a set of picks that lines up with the move out curve that I just plotted. And not only that, those picks are close to each other. They're on nearby stations. And yeah, that is true. Like it's really pretty subtle, but for instance, let's take this one on the left-hand side. When I add it, it's these picks, these ones and these ones. Probably those ones too. Boom, boom, boom. And that's the event. And yeah, but it's kind of cool because we're basically going from the reference catalog, which is this, to these, somewhat enhanced catalogs, this and this. But we're pretty sure that we're maintaining mostly realistic events, even when we do that. Like probably above 95% realistic events. And yeah, there's other cool things that we can see in the catalog. For instance, we can see quarries, mining blasts, and I'm highlighting a few right over there in the Central Valley. What's interesting is the NCEDC catalog does not report any events at these locations, like 0. But we clearly see, both in the satellite view, that there are quarries there. We have concentrated seismicity at these places. And there's a few more we get in Southern California, or close to Southern California. Those ones, they do report some events. Either way, we get them as well. And we know they're quarry blast events, not only because there's a quarry there and we have the locations that are precise, or pretty precise, but if you look at the time of day that the events occur at. So it turns out that, most mining operations have a pretty fixed schedule. They kind of set off their charges at basically the same time of day, every day. And these time of days are in UTC time, so it's a bit shifted. But that bullseye you see, that's the working hours of the day in California. So to go to California time, you have to subtract 8 hours and you're basically at noon. So in each of those quarries, we can kind of identify those. And that may seem a little tangential to talk about earthquakes and quarries, but there is sort of a lot of efforts involved in being able to detect both and differentiate them. So that's why we're accounting for that, thinking about it anyways. Lastly, or last few things, we can improve our initial earthquake locations using something called double difference earthquake relocation. So you build the original catalog, and then you can kind of relocate all events with respect to each other by solving a different optimization problem. You're minimizing what is called the double difference residuals. Kind of a weird concept, but essentially it just means you're able to cancel out some of the uncertainty and then localize the relative positions of events. So here's just some examples where the left is the initial, the right is the relocated. And you can see what it does is it improves the resolution of the faults. And this isn't perfect. This is kind of an ongoing effort, but it's definitely nice to see that there's post-processing that can be done to improve things as well. So there's that. There's a zoom in. That's the San Andreas fault right there in the middle. There's more of the San Andreas in the middle. Calaveras fault growing up on the right-hand side there. Yeah. This is the Mendocino triple junction. So you get that kind of cloud of seismicity up there, and it kind of concentrates once you do double difference. So from like an interpretation standpoint, it is very helpful having precise event locations. So a lot of times the initial ones aren't quite good enough. That's why we're doing this. So the big picture is we want to extend this catalog to 20 years, like all of California, for what we've shown. 20 years, do the double difference, and just have like a good like reference catalog that we can rely on as kind of like a new baseline in a sense. Here's the Sierras. Here you get those little clusters just kind of concentrate. You see that? So they just kind of narrow in, and that's what we like to see. There's a zoom in even more. And one thing to keep in mind is all these places I'm showing you, we have totally different like station coverage in each of these places. Data quality is different. But we have one algorithm, but we didn't really have to tune for any of that because we just have our graph set up, and it's able to learn how to process each area differently on its own because it kind of sees the graph structure that's locally different and it accounts for that. So I think that, even though these catalogs have been produced over these large areas before using the routine methods, they have to do kind of a lot of specialization for each area. There's like different velocity models for each area, sometimes different thresholds they have to apply, different processing routines. But we're kind of getting away from all that. We kind of have, like, in some sense, a method that just kind of is able to handle that heterogeneity on its own. And that's kind of the strength of it. And it's just me doing it versus, like, the routine approach is a lot of people involved. So just as a final thing, we've started to compare our method with a different associator. And the gamma associator is sort of widely used right now, although it's quite recent. And it's different entirely. It's not a deep learning model. It's just a clustering algorithm where it kind of does what I was saying, find sets of picks that look like they correspond to a theoretical move-out curve. And what's cool is, in fact, they can give really similar result with one very major caveat that I'm about to say. But with that caveat accounted for, the left-hand side and the right-hand side are the two catalogs. They've actually done theirs. We're working with Wei-Chang Zhu and student Bo Rong. And they've extended it. They've also included Southern California. But the caveat is that the initial catalog does not look like this at all. The gamma catalog initially outputs something like 2 to 3 times this number of events. And then they have to filter those events to find the real ones. And how they did that, interestingly, is they had to find which ones have sets of stations that make no sense, have been assigned to stations that don't have a geometrically reasonable pattern. Essentially, the gamma output is not giving you a geometrically consistent set of associated picks for each event. It does give you the real events too. It gives basically the real events and a lot of false events. And importantly, and thankfully, they did find a way to sort of identify automatically those false events. Once you account for that, the two approaches are pretty similar. We think it's still a little bit of a downside to have to do that because when you do that, you're going to also throw out some real ones. Like, it's a little hard to tune this quality criterion that they've engineered. But surprisingly, once you do that, they're pretty similar results. I'm going to basically just skip through this. This is just comparing the magnitudes we get from both methods. But also, if you look at the event count and time from the two methods, they pretty much match up quite accurately. So it spikes up and down because, there's a big earthquake and you have some aftershocks, and then it goes back to background rates, and then another big earthquake occurs, and so forth. But I was not expecting this because I'd kind of come to the conclusion that gamma is not going to work on these scales because I understood that it outputted a ton of false events. But they were able to make that filtering approach work and throw out the false events. But the irony is that what they had to use was some notion of the geometry, the relative locations of stations, which is exactly what our graph neural network is using kind of in the first place. So yeah, with that, I'll just conclude. Yeah, we think this model works for earthquake detection on this large scale with hundreds of stations. That was about 900 stations. And we can get an increase in event rate by about 4 times right now compared to the NCEDC catalog. It's probably a function of the picks. So we could probably go to higher if we got a better picker, maybe go to 8 or something with even more picks. But yeah, and then just in general, I think graph neural networks are a very powerful tool for this non-Euclidean data processing challenge, which is very relevant here, but probably in lots of other problems in geophysics as well. Yeah, thank you for your attention.
So you said
Yeah.
is there a reason why
Essentially, I wanted to do it. First reason is I wanted as a, basically I wanted to check if we train it to detect events anywhere, once we apply it, is it going to detect events only at the real faults? That was like a huge, I didn't want to bias it ahead of time. You could bias it ahead of time. You could say, let's only train the real events. And then, yeah, it's probably going to get even better at detecting the real ones. But this is kind of like a proof of concept. The proof of concept is it's able to detect events anywhere, And so once you apply and you only are getting them at where we expect them to be, it's like a huge confirmation that it's working. And the other reason is you do want it to have some ability to detect events everywhere, because there is occasionally going to be the one-off event that's just not near a fault. Maybe it's something else, a blast or something. And we want our model to be able to detect them anywhere. But I do agree with your point. We could probably add in the real data as well, maybe find the best of both worlds. Yeah. Yeah.
Does that mean that I guess, how sensitive are you to how well you understand the block?
Yeah, not that sensitive, but I think we're sensitive in the exact same way that kind of all the algorithms are. Like, we're going to assume a velocity model, which is not going to be the true one. Like in this case, it's just a 1D model for the whole region. And so, yeah, it's somewhat sensitive in the sense that the real events won't correspond to that. But it's kind of the same sensitivity you have when you try to locate an event anyways. Because when you try to locate an earthquake, traditional methods, you're going to have to assume a velocity model. And it's again going to be wrong compared to the real one. So that same disconnect appears in just regular earthquake location. We're just encountering it again. But basically, to add on to that, in the synthetic data, I had a lot of noise to the arrival times and even some like systematic biases to the travel times, like 1 or 2% shift in one direction or the other. So it kind of knows ahead of time. Don't always expect the picks to follow this theoretical move out curve that I'm telling it perfectly. It knows there's going to be deviations from this theoretical move out curve. And that is kind of important to tune, because if you apply it somewhere, the velocity model is very different. It may fail unless it was understanding ahead of time there could be these biases. So yeah. Go ahead.
What happens at a station or
put
out some additional stations?
Yeah. Thanks for bringing that up. And I should have emphasized this. We don't. So the graph neural network allows you to add stations, remove stations. And in the training process, we're already simulating tons of different combinations of stations. So essentially, I have my reference set of stations, which is all of the ones that have essentially ever existed in Northern California. But in training, I'll either use all of them or a subset. And I just kind of sample sort of randomly. And the thing is, graph neural networks, this is kind of a remarkable aspect. They're actually, the number of trainable weights in the GNN is independent of the number of nodes. So it's learning something how to act on graphs, meaning a graph is an input to the GNN. So I can give it different graphs in the input. Like, this is what they're good at as well. So the answer is, yeah, you can add in new stations, you can remove stations. There's a point where it'll probably break if you end up so different than any of your training data. But I mean, it can be different than the training data. Like, I could just add a station, it won't cause an issue. And the reason is again, you make the graphs that knows which ones are talking to each other. It's like a kind of dynamic thing, right? Like, I added some stations, but it's already going to do the right thing because it connects them together. And yeah, they're just trained for this generality. It's very different than normal neural networks, which you might have like a fixed number of weights that's a function of how many stations you have. So you're stuck with it. We don't have that. So like in this case, sometimes I'm training with like 300 stations. Sometimes I'm training with 900 stations. And it's learning a model that can be applied to either case.
In terms of the association, how about using relative?
Yeah. Right. This is a very key point. And like, yeah, like gamma tries to use amplitude as well. That's kind of one thing that gamma is doing. And we think that in general, the amplitude should be useful because, yeah, there's an expected pattern of amplitudes. In some sense, we're using it like kind of as a quality control after the fact, right? We're saying, do our magnitudes make sense, which is a function of the amplitude. But yeah, you could add the amplitudes in the input. The only reason I haven't done that yet is because you then need your synthetic data to also accurately match the real amplitude data. So the thing is, with like your point, it's kind of easy to make synthetic arrival time data that you're not super sensitive to like the absolute values, like your plus or minus, a few fractions of a second or a second. That's not a problem. With amplitude data, it varies so much. Like each station correction is different. There's side effects. So my fear is, and the reason I didn't do it is, if I train it with synthetic amplitude data that's very different than the real amplitude data I'm going to encounter, now we might have a problem. Exactly. I could train the real data and then we'd be good. So yeah, and the amplitude data will probably help a lot, like especially in aftershock sequences when there's like tons of events. Like we've shown that we can still separate pretty dense aftershock sequences, but I do think having the amplitude data as well will make it even easier.
Then just real quick, you say something about the depths.
Yeah, I didn't show any depths really. Basically, we're just getting pretty consistent depths with the NCEC catalog. To depth is yes, yes, yeah. In this case, yeah. The neural network outputs a heat map that is both map view and in depth view. Yeah, I just didn't show the depth aspect. Yes. Look to the people to your left. But I think it's a long, ongoing process. But I mean, there's interest, but whether it'll happen or how long it'll take to happen, we don't really know. But I would love to see that. Like at some point, they should have the NCC catalog should also be this complete, right? It should go down to this lower magnitude completion, but it should be the one you can download straight from online every single day, you know? But that's probably like 10 years away or something. I do think so. So like I can kind of tell that the limitation we have now, interestingly, is the picker. So how it went kind of historically was the pickers got good and the associators were the limiting factor. They weren't good enough. I can kind of tell that in some sense, associators are now good enough. Now when we see that it's not working for like a little event, it's because we don't have enough picks for that event. And so I do think that now the next thing to improve is the pickers, and at least for me, and there are ways to do that. So in fact, what I'm most excited about is, you know, normally traditionally pickers are done one station at a time, but there is this new model two have come out recently that they use graph neural networks for picking. So what they're doing is they're now combining stations to do the picking, meaning each station can communicate with each other. And what that does is if the signal to noise ratio is really small on one station, and so you're not sure, but it sees another similar looking signal on another station nearby, now it can be more sure. So I don't think we've reached the limit because these graph neural network based pickers haven't really been widely implemented yet. So yeah, that's my idea. Yeah. Sorry.
Go back to your histogram,
This?
the one where you were comparing the types here.
Okay.
Yeah. So I noticed that most of the spikes here, gamma has more than G.
Yeah.
Except for that one.
It's a good point.
Have you looked at these, like why? Depend on the geometry.
It definitely could depend on the geometry of the stations. There's different sensitivities in different areas. I didn't notice that one you pointed to where we have more than them. I'm not quite sure what's going on there, but where they have more than us, that's probably the sign that they have the false events. Yeah. Because I mean, and it's not just us that have seen that. Other people have looked at gamma, and a lot of people are kind of reporting it outputs a fair amount of false events. And I only just learned recently that this filtering approach is possible, where you can kind of get rid of most of those false events. But yeah, and if you didn't do that, it'd be even worse. This plot would look even more different. And now the answer of why we might have more than them could be that we're a little bit better in like the Sierra Nevada range than them, because our model is a little bit better at sparse networks than gamma. So in the areas where there's sparse station coverage, ours seems a bit better at getting events. So I could check though, and I should. Yeah, it's just one. Yeah, that would be my guess, is that there's like a single main shock aftershock sequence in some area that's kind of sparsely recorded by the gamma, or by all the stations.
I noticed on your other plot that have more events in Northern California.
Yeah. Yeah.
So question, have you looked at the waveforms? And second, operators of that network about why they're missing.
Yeah.
This
Yeah, I completely agree. I think what's actually going on is just that our magnitudes haven't been totally calibrated to the same scale precisely. Because in their catalog, they use like 3 different magnitudes, like duration, local, and moment magnitude. And those things don't always line up perfectly. So they have kind of like selective reasons why they use one versus the other in different time for different situations. In our case, we only use the local magnitude for everything. And so we try to calibrate it essentially with like linear regression so that our magnitudes match with theirs for the matched earthquakes. And I just think it's not perfect. And see where they start to use moment magnitude is basically this point you've identified at like 2.5 to 3.5 onward. There's this transition where I and that's my guess is that their magnitude scale has changed and ours hasn't. So you get this deviation. And yeah, like I think yes. So the blue has 3 different magnitudes they're combining, depending on the earthquake. We only have one type of magnitude. We already know that it's hard to make these magnitude curves line up perfectly. So it's not surprising there's some deviation. Yeah. So, but it's still a somewhat of a point of suspicion. We have to be careful, but that's my understanding. And the reason why I kind of trust our result is because our curve is very straight, and that's also what we expect. So even though it's a little larger in that area, it's straight everywhere else, and it kind of lines up with it in most other places, like down here, up there. So it's probably okay, but yeah, I mean, it deserves some looking at. And also, that was the initial one. The updated one I feel is like a little bit better, but yeah. Yep.
One quick announcement was that the department office upstairs on the first floor will close at 2 o'clock.
Thank you.